And one of the products that Mezintel supplies is the portable depth tracking system for directional drilling applications. Today's topic of interest is in regards to verifying encoder accuracy and repeatability. This is a QA, a QC procedure that we do here before we ship the combined encoder and the interface box or the instrumentation box. The picture you see on the left is the minimum configuration of the Mezintel depth tracking system, which is composed of the gray interface box, also known as the instrumentation box for data acquisition, and then there's the hook load sensor and the encoder. On the right, there is a magnified view of the encoder, which is basically a rotary sensor. And what Mezintel does, it converts the rotation signal into a linear movement of the drill pipe, and henceforth the bit depth. The green arrow just points to the fact that today's focus is on the encoder. So how do we go about verifying encoder accuracy and repeatability at Mezintel? We do what we call a fast encoder rotation test, and this one proves that the counts are accurate and that the counts are repeatable. On to the next slide, and this one is in regards to setting up the encoder for the rotation test. And again, this is for the depth tracking system, and this is a three-step procedure which is illustrated henceforth. The first step is to locate the clamp on the eye of the encoder and to insert a 5/8 inch socket wrench, and this one can be clamped down with an Allen key, as you see in the picture there. The second step is to align, is to put a marker on the rotating part of the encoder and to line it up with another marker on the housing of the encoder, and this one will be marked as the initial position before we start doing the rotation test. And step number 3 is to verify that the encoder counts, the encoder initial counts are 10 million, and this you can verify using the software. So the depth tracking system as supplied by Mezintel, once it starts up, it will start with the default count of 10 million, as you can see there. So this 10 million will now correspond to the initial position of the rotary part of the encoder, which is lined up to the housing. And this can be arbitrary. It can be at any point, as long as you do have a lineup of the rotating part and the stationary casing, then that will do. And then observing that the counts is a nicely rounded number, like so, which is 10 million. Okay. So on to the next slide, and having completed the encoder setup, this slide is going to show how to do the fast rotation test. We're going to look at some specs for the equipment that's going to be used in this test. And the encoder is one with pulses per revolution of 1024, and the counts per revolution translate to 4096. This is just 1024 multiplied by 4. You get this value right here, which is counts per revolution. The power drill used to do the fast rotation test has an RPM capacity of 3,500 pulses per revolution. The data acquisition system, which is standard in all the Mezintel depth tracking systems shipping now, is the MCC DAC 1808 24-bit resolution with a specific FPGA encoder programming for the counts, for acquiring the counts. So there's a fast real-time clock that does that with the FPGA programming. So on to the video, and what I'm going to do here is just to play the video that explains how the test is done. The fast rotation test is done on the encoder and how the results are interpreted. So here we go. Right, so after presenting those setup instructions, we are now ready to do the rotation test. And what do I have here? I have the encoder, and the encoder has the rotating part, um, and as well as the housing of the casing of the encoder, and the markers are lined up at this point, and this is the starting position. The counts for the starting position are registering as 10 million counts right there, and so now I can go with the rotation test. On the side of specifications, this particular encoder is a 1024 pulses per revolution encoder, which means that the counts are times 4, which gives you 4096 counts per revolution. You can prove that by just rotating the encoder in the clockwise direction so that you get an increase, and by the time I go to my initial starting position, I should get 4096 counts right there. So if you look at the alignment of the encoder at 4096, it's pretty much back to where it started. Okay, and I can, at this point, I'll just go back so that I get my initial starting counts, which is a nicely rounded number of 10 million counts. Right? So right there, I'm going to go back to the 10 million mark. So it's very sensitive because of the number of counts that I get per movement, per degree of movement. That's why the counts are increasing very rapidly there. Okay, so it's going to go one count forward to get. There it is. Right, so right now I'm going to do the rotation test, and I'm using a power drill, and this particular power drill has a revolution per minute capacity of 3,500. This is at the fastest setting, which is setting number 3 that I've used here. And I'm gonna make the power drill with the socket wrench over here, and I'm gonna increase the counts by going in the clockwise direction. So I'm setting up my power drill to go clockwise, and you can see the counts have already started changing because I've left the starting position, and I'm going to go clockwise way past 10 million, like so. Then I'm going to go anti-clockwise, and I'm going to go below the 10 million mark so that I go past that. And now I'm going to try to go back to the 10 million mark and to see what position the markers will be at. So I'm going to go clockwise again. And once I hit 99, I'm there. Okay, so I'm going to do a fine tuning using my hand, and I'll just try to get the 10 million count, and then after that I'm going to try to see what my markers are showing. So I'm focusing on the counter there, and to see that once I get the 10 million, what is going on with the markers. And as you can see, the markers are lined up perfectly right there. So what this means is that although we were not able to count how many revolutions we went past the 10 million marker or under it, just the fact that we were able to get back to the initial counts of 10 million, and then the markers line up, there's a very high probability that the encoder worked properly. It did not lose any counts, otherwise we wouldn't get this alignment working. And the data acquisition was able to collect the samples or the counts fast enough, not missing any, so that it was able to register the right value in the software. So this is the test that we use to pass the encoders over here at Mezintel when we bundle them with the depth tracking system. And this test gives us full confidence that the encoder will work properly, it will be repeatable, and it will be accurate in the field. Because in this case, we have assumed that the drawworks will rotate as fast as 3,500 revolutions per minute, which is a very fast rotation. Normally during the drilling process, the rotation of the drawworks is not that fast. as you know, because of the very slow drilling that happens. However, when the traveling block goes up to pick up a stand, that's when the rotations of the Drillworks drum are pretty fast, but not as fast as 3,500 revolutions per minute. So this one gives us a good safety factor that the encoder and the data acquisition system and the data acquisition system, which in this case is the NCC DAC 1808, will perform properly, will perform well, reliably and repeatably when used in the field. And this concludes the rotation test for the encoder as done here at Mezintel to pass our depth tracking system for field use and shipping to our customers. Well, thank you for your time in observing and listening to this presentation, and we'll see you in the next presentation.